All right, today's lesson, Chapter 9, Part 2, Symmetry and Dilations. First up, a little bit of vocabulary. Line symmetry occurs when a figure can be mapped onto itself by a reflection in a line. The axis of symmetry is the line in which the figure is reflected across. So I'd like you to draw that rectangle. And this rectangle would have two axes of symmetry, one that's going to run horizontally, and then another that'll run vertically. Either of those would split the rectangle into two congruent parts, so they would be considered axes of symmetry. As long as there's one axis of symmetry that would split the shape into two congruent halves, it's considered to have line symmetry. So line symmetry, again, you can map it onto itself by a reflection in a line. So in other words, there's some line that you can draw through it that splits it into exactly two parts. And that line is referred to the axis of symmetry. So we're going to look at each of these four. These you can just watch. I don't feel like you necessarily have to write these down, but what you'll be doing later on the assignment is you will look at each one of these, and then you will determine if it has line symmetry or not. If so, I'm going to ask you to draw all the lines of symmetry and then state their number, which would be how many did you draw. So for our arrow here, how many do you think? Just one is correct. So there is one line of symmetry that splits it just like that. And then we could fold it in half and it would be identical, congruent on both parts, the top and the bottom. Any other line that you try to draw will not split this into two congruent parts. Next one, let's look at Pac-Man here. Pac-Man does not have line symmetry. Even if he was kind of even, if I tried to draw it through there, kind of through his mouth, the eye wouldn't end up down here, so that doesn't count. So none at all on that one. And let me fill this in before I forget. So the first one, we would say yes. And there's one line of symmetry. Our circle, think about how many, if any, that would have. Think on the circle. Circle, I could split there. I could split there. I could split there, and I could keep doing this forever, and I would never run out. Because anything that goes through the center of the circle, which would be like a diameter, would be an axis of symmetry for the circle. So the circle most definitely is yes. And then what I'd say there for how many, let's just put the infinity symbol. There are an infinite number of axes of symmetry. It's a little bit neater than my first one. And last one, the parallelogram. So take a little bit of time to look at this one and think about if the parallelogram would have axis symmetry or not. So usually what I hear, the first reaction is, yeah, you could split it along the diagonal. So let's say you think about doing that. While it is true that that does split this into two congruent shapes, they actually wouldn't be on top of each other. Because if I tried to fold this down, this edge here, when I go to fold it over there, it's going to end up overlapping and then running over the edge as well. So they're not going to line up exactly. So while that does split it into two congruent pieces, they're not going to line up the way they would need to. So we would say for both Pac-Man, no, and no to the parallelogram. That line doesn't work. Because when I go to fold it, that part ends up down there, so it's no. Another type of symmetry is rotational, which is also referred to as radial symmetry. And when we're rotating something, we're turning it around. So when a figure can be rotated less than 360 degrees about a fixed point, so that the figure looks like it did in its original position. So what I've got a little GIF of is some kind of molecule, probably some kind of carbon and hydrogen molecule. So you've got the carbon centered here, and then the three hydrogen molecules are spinning around. And at every 120 degree placement, one of the hydrogen molecules is lined up again. So it's not saying you can spin it however you want to, it's just saying that there's some rotations that when you turn it, it's in the exact same position it originally was. So this one definitely would. Every third turn, you could think about it that way, gets you back to where you started. And some extra stuff about rotational symmetry. Let's do this just a little bit at a time. So the order of symmetry is the number of times a figure maps onto itself as it rotates between 0 and 360 degrees. So basically saying as you're turning it around, how many times does it overlap where it started? So for that molecule that was on the last slide, the order would be 3. One example of this, let's say we're looking at this pentagon. Often, if they're kind of a regular shape, however many points there are is going to be what the order would be. And to kind of verify that, as I go to rotate this around, there's 1, 2, 3, 4, 5 gets me back where I started. So there were 5 turns that looked like the original. So the order on that one would be 5. And for regular polygons, at least, however many points there are, that's always going to be the order. When you're dealing with some kind of irregular shape, that probably isn't going to work out, but it does for regular. And related to the order is the magnitude. The smallest angle through which the figure can be rotated to have symmetry. So in other words, how far do we have to turn it until it looks like it did to begin with? How far do we have to turn it until it looks like it did to begin with? And that's not as easy to eyeball. So the 5, you can kind of just look at it and probably figure that out. The magnitude, there is an equation that we can use to kind of go backwards to find it out. So the magnitude will always equal 360 divided by the order. And if you think about that, I hope it makes sense, that 360 would be the entire rotation, all the way around, divided by the order is how many turns we made. So if you take the total, divided by how many you did, you'd find out what each turn was. So for our example, if we take 360 divided by 5, we'll get 72 degrees. So the meaning of that is, if I go back and I rotate this again, that rotation was exactly 72 degrees. This one was also 72 degrees, and so on, and so on, and so on. So these two, this is what I'll expect you to do on the assignment. Directions will read, determine if each has rotational symmetry. If yes, state the order and the magnitude. So for the cross here, I would say yes, it definitely does. And then we can do it, or you can just look at it, but there would be 1 turn, 2, 3, 4 gets me back. So the order is 4, and to get our magnitude on this one, you could probably just realize that it's 90 degrees, or we could use the equation and do 360 divided by 4, because that was our order, and that would also give me the 90. And then the lightning bolt would be no. We can try it. If I spin this around, that doesn't line up, that doesn't line up, doesn't, and it doesn't line up again until I get back to where I started, and that doesn't mean anything, because every object would be the same after you rotate it 360 degrees, so if that's the only one that works, the answer is no. So if yes, on the assignment, make sure you give me the order and the magnitude like I've modeled for you here. Symmetry is not restricted to just 2-dimensional objects, so it functions pretty much the same way if you're dealing with 3D stuff. So instead of line symmetry, we would call it plane symmetry. A figure can be reflected in a plane. So go ahead and draw this rectangular prism. And with this, we're just going to be saying yes or no. So for this example, if I sliced my prism with a plane, like I cut through it horizontally like that, I would get now 2 smaller rectangular prisms that are congruent. I could also slice it vertically. So if I cut it all the way through vertically, those would line up. In this case, we could also slice it that way. then I would end up with two triangular prisms that are the same, and there's a whole bunch of other cuts that I could make as well. For these, we are only concerned about yeses or nos. So if it has it, you'll say yes. And then there's also axis symmetry. The figure can be rotated onto itself. So we're just thinking about, can it be spun around and it look the same? So for this one, if I were to put an axis right through this center, and then I rotate it around, it would look the same as it did to begin with. So on the assignment, the directions will read, does each figure have plane, axis, or both? So you've got four potential answers there. There might be none at all, so you could say none. It might just be plane, it might just be axis, or for some of them, like either of these actually, it would be both. And there's no numbers associated with this kind. And then this next and final thought for the day is an extension of what we did last time with the reflections, translations, and rotations. To perform dilations, and we might want a little bit of a reminder here, a dilation can either be an enlargement or a reduction. So we talked about these a little bit in chapter 7. Can be an enlargement or a reduction. So dilation just means there's a change in size. So these transformations are not congruence transformations, they are similarity transformations. And it's a little bit like a translation from last section, but instead of adding the vector, we are supposed to multiply by the scale factor. So whatever scale factor is being used, whether it be an enlargement or reduction, you multiply every x and every y by that. So here's an example. If the original point is xy, and my scale factor is, in this case, k, I would rewrite it as k times xy, comma k times y. So again, kx, ky. If it's a fraction, the number will decrease in size. If it's a whole number, it will increase in size. And then you plot those points. So the final thing that we are going to do today is example 3. These will be 3-point questions, just like what you did on... All right, so like the last ones, our first step is going to be to graph the original image. So we are going to plot on the coordinate plane, and like last time, the grid will already be on your assignment, but for in the notes, just go ahead and sketch one. A is at 9, 9. So we're going to go 9, 9. Label that as A. B is at 3, 3. So we will place that there. And finally, C is at 6, 0. And then double check to make sure we didn't screw anything up. Looks good. So we will play connect the dots. And I don't want that to be yellow, do I? Let's try that again. Play connect the dots. And there's our original triangle. So then our new one, we're going to write those out. So we're going to still list it as A prime, B prime, C prime. And like it said on the last slide, we're going to multiply every single coordinate, both x and y, by our scale factor. So in this case, a third. So if we do a third of 9, that's 3. A third of 9, again, is 3. B prime, a third of 3 is 1. A third of 3 is 1. And then lastly, C prime, 1/3 of 6 is 2. 1/3 of 0 is 0. So to get our third point, we are going to graph the points we just generated. A prime is at the same location as B, and that's fine, so we'll just label them both. B prime is at 1, 1, and C prime is at 2, 0. And then we will again close the figure. Obviously, these two aren't congruent. They're not supposed to be. It's a dilation. In this case, since r was less than a 1, it had to be a reduction. So if I start there and go there, it looks way smaller. But the shapes do look similar. It looks like the angles are the same, and the ratios kind of look like they match up. So that's a good sign that things were done right. So if any of this was too fast or you need to see it again, please don't hesitate to ask the sub to go back, or you can rewatch the whole thing since it was only 15 minutes long. And then expectation is that you will work on the assignment that you're about to be handed until you are dismissed. There will be a test over this material on Tuesday. And I know I had mentioned something about that you could make a cheat sheet. After thinking about it, I'm just going to let this test be open note. So make sure on Tuesday that you bring your notes with you. You may use the notes from last time and the notes from this time on that, but no homeworks or anything else like that at all. Just the notes are what you can use on there, and then you should be fine. All right?